Hello guys, welcome to Root and Route. Today we are going to continue with the Rust CLI engineering part 2, and we are going to dive deeper into XORing and AES-GCM, how both algorithms work and how to implement it using Rust. If you are familiar with XORing, you can completely skip this part. I just wanted to start with XORing because AES-GCM also does the same thing internally, so you should be or you must be able to understand how XORing works, and not on a single byte of key with your input, but how it works for a stream of bytes. So let's start with the foundations of XOR encryption. As you know, it's an exclusive OR. It's a logic gate that returns true only if the two inputs are different. That means if you have two inputs A and B, and if both are 0, it always returns 0, and if both are 1, it always returns 0. Only if any of the A or B is 0 or 1, it returns 1. That's how it works internally. That's a logic gate of XOR works. So it has a magic property. It's called self-inversion. That means if you XOR a value with the same key twice, you get the original data. So if you have ever implemented XORing in any language, normally we don't do a decryption separately, because the same function that you use for encryption can do the decryption for you. That's the magic of XORing. So how it works and how what's the algorithmic part of this one. Let me explain that. Before that, let me reduce the size of this to a bit lower. Yeah, this is a sequential alignment of normal XORing. Imagine if you have a message called encryption, and if your key is secret, that means your key is less than the input message that you are giving for the function to encrypt. So how it works is, as you know, a string is represented as a stream of characters, and it stores inside an array in memory. So, and the index always starts with 0. So you can see the input message has a length of 10, but the index is starting with 0. Then the key has the same, the key is saved as the same kind of how the input value is saved in memory. But if you can see this, the key ends at the index 5. That means after XORing every index, like first it does with E XOR S, then N XOR E, and it continues that up to P. And when it reaches P, it after XORing it with T, there is no key left. So what to do in this stage? This is a important algorithmic part here. So we reset the key, we restart from the key once again from the S. That means again it goes back to S, Z, S, E, Z and R. Then again it does the same thing with the rest of the input strings, input characters, and once the input character length is done, the encryption will be finished. So this is a way the stream of characters works when we have multiple bytes or multiple characters of key for XOR encryption. And how to achieve this in programmatically? Yeah, of course you have to use the modulus operator, the modulo operator, and this is nothing but it's a division, and it gives you the remainder of a division. And the important thing you have to notice here is the logic behind this one is you have to iterate through all the input characters. So the iteration should be from 0 to length of the input. Then you have to do a modulus operation on with the index and the key length. Key length here is here as an example it is 6. That means 0 to 5. So every time you have to do the operation. As an example, if you do 6 mode 6, there is nothing. As a reminder, it always gives 0. Then if you does the same with the 7 mode 6, you can see it returns 1. Why? Because we just take only the integer part of this. The actual floating point number may have more decimal values after that, but we just take only the integer part of that. That's a key algorithm secret of multi characters for XORing. So this is a rule we use. We use key index equal to current index modulus key length. This is always be the core secret of do XORing with multi-character key values. So how to achieve this? That we are going to do now. So let's start our REST code for doing the same. So let me create a. So meanwhile, while we are continuing this one, we may go through some new stuffs here in this one that is necessary for building your CLI apps. Maybe some new concept in REST, and maybe something. I always expect something new will come in between to explain. So XORing, I just created a project. And one more thing, I'm going to achieve the XORing manually, not using any of the REST built-in functions, because I didn't cover the REST built-in functions till now. I will cover in one of the videos that I'm planning. The first thing that we are going to do it manually. Manually means just plain text algorithmic way how to achieve this. Before that, just because it's a CLI engineering tutorial, so what I'm planning to do is we can make it in a way that we supply the user string, input string, and password through command line argument. So we can learn how to get that command line argument. So that will be something new that I can share with you now. Just do a skeleton first. Okay, just try to implement our XOR function first. XORing, don't mind the A recommendations. So XORing, what we need is we need two inputs. The first is the actual input that we need, and I'm going to give it as a string that we already discussed on my last video, and key is always the same, the string. Then what I'm thinking is returning as this string as the output of this function. I'm not taking any suggestions from the AI, and it's okay to take suggestions from the AI, but if you are learning, if you are a beginner, don't take it, because you won't remember anything after some time. So try to do it yourself. So at least you can memorize things, because you are learning a new language. You should be familiar with how things are done in a new language. So I recommend you to do it manually initially. Then if you are familiar with the stuff, so you can definitely take the AI suggestions. So what we are going to do here is we are going to achieve the same thing that I explained here using this one. So you have to go through each and every characters from the input string. So what you have to do in REST for that is let just say input characters equal to input dot bytes. I think you can convert this as bytes, so that will give you every byte of this. This we don't need this. every byte of input characters now, and let us do the same for the key. Now we have both input and key characters. Now let me take the length of the key as key characters.len function that we need, because in our algorithm we have to use this one, like current index mode key length. So we are taking the key length. The next thing we need is let input underscore len. Yeah, this is, you don't need to take it separately like this, you can directly use it inside the loop, but I'm just forcing it because just be familiar with how the variables are declared in Rust and how the mutable and immutable stuffs are done. So you just try to do it manually most of the time initially. Once if you are familiar with all the syntax stuffs and other things, you can directly use it anywhere. Like instead of taking it as to a variable, you can directly use input characters.length in a loop itself. Nothing wrong in that. So the next thing I need is a mutable variable. Yeah, you can call it XOR. I'm going to call it XOR bytes. So yeah, it's going to be a vector, and vector is I already mentioned vector on my last video. Vector is created inside the heap, and stack will have a pointer to the vector. So you can create the vector two different ways, either using the new or with capacity, and you can specify the capacity here. You can mention it as input length, so it won't, we don't need to, you don't want to do very dynamically. You can just specify the capacity, because the XOR byte will be byte's length will be having the same length as input length. So we know that, so we can easily declare the XOR byte length as with the capacity of input length. So the next thing is, as now we have all the required stuffs, like we have the length of the input string, we have the length of the key string, and we declared a new dynamic place where we can store the XOR bytes. So the next thing we need is we have to iterate over iterate over the input string. So for that I'm just doing 0 to input length. So what exactly here we are going to do, we are taking every byte from the input. So I'm saying let input underscore character equal to here I'm taking why it is showing error. Did we do any syntax issue here? Wait a second. No, something wrong. No, for I in 0 to input length, let input underscore character equal to input characters of I. That means we are taking the first byte when I is going to be 0, we are going to take the first byte of the input string. So, and now what we have to do is we have to do the same thing for key characters. So you can either apply the directly as the AA suggests, but I strongly recommend to do it in your own way, or like at least just try to type it to be familiar with what you're doing. Here is our algorithmic part that we discuss here. We are doing the current index modulus the key length. So we take the key character. That means when the index is going to be 0 and is going to do a 0 mode 6. So I mean not always 6, but in case suppose it's as for this example, if it's going to be secret as your key, then what it's going to done is it takes the first character and the first index 0 mode 6. 0 mode 6 always retain 0 because there is nothing to do on the division or remainder. So when if there is no remainder, it returns the first number. If it's the first number is less than the number that's going to be divided. So that's how the internal things of modulus operation works. So you can iterate over it like this. So once it reaches here, then you can restart it here. So we just did the same, the main algorithmic part here. The next is going to be the XOR character, that is the input character. This is the caret symbol is the one that is used to do the XORing. In Rust, I think not only in Rust, most of the programming languages, this is the one that is used for XORing. Now we have the character, the input character, the key character, and now we XOR the character. It did fill it for us. Now we need to add our XOR character to the vector that we already created. So we are just pushing that to the vector. So I think this is okay, and of course I think it's showing the error because we didn't return any stuff. So this loop will handle the XORing of the input string with the secret, with the password that we supply. So what we because we set it return type as a string, we have to return the string from this one. So there's a function called string from UTF-8. We can pass the vector, and you can unwrap. The unwrap will actually this is not a Cipher method. And why? Because unwrap can fail, but here we know exactly what we are doing, so we can do the unwrap. There are a lot of issues when you're blindly using unwrap in Rust. And if you come across the latest news that happened in Cloudflare, it was because of the unwrap, because unwrap has a lot of stack unwinding issues related to that. So if you are not sure on something to unwrap, don't use it. Try to handle it separately and safely checking the return result type and error type. So here we know it, so that's why we are returning it. And in Rust, as I explained already in my previous video, if you want to return a value, actually you can either use a statement without the semicolon, or you can use return keyword then a semicolon. Both will do the same thing. So is there anything wrong here? I think now it is fine. So now we have the XORing part done, and we got the result back. As I explained, the XORing can be there is no need of any separate decryption for the XORing, because that's what I explained already. The magic is the inversion. If you do the same ciphertext once again with the same key, you will get the plain text. So here what you're going to do is we just make it dynamic. Like we're going to take some arguments from the user, because it's basically is going to be the CLI engineering here. So what we do is we make it a perfect CLI application. So let the arguments is the arguments you can, I mean the command line arguments you can access using ARGS, and it's very simple. Just say collect. Either you can convert it using this, the time of collecting you can convert it using this, but the better way is always use here vector of string and then say collect. So now we have, see, the AI is suggesting too much for me, but don't take that. Now we have the arguments in a vector of strings. So the next thing is we just check if the argument length, what we are expecting is less than 3. We need an input string, then we need a password. That's it, right? Yeah, then it should be 3, because the first argument is always the 0th argument is always the program name itself. So there should be argument 1 and 2. So the length will be 3 normally. So if less than 3, we just say usage, and yeah, argument 0 is your program name. So this is correct, and if it's not working, it returns, and if it works, yeah, here, oh my god, I didn't know that the AI was filling this part. So we take the input string from the argument 1. Cloning, we already discussed the clone part on last video while we were discussing about the ownership. The actual argument is a reference, in fact, if you ask me. Either you can take the reference of that and then you can convert it, or we can do the other way itself. Now we have the actually when we take this one, see, the type is string and here the key is string, and there's an implicit conversion between this string type, like, see, we are passing a reference of this string type, but our method is accepting this string. So what you can do, either you can pass it, because Rust is implicitly handling these two for us, it won't make any error. But for your clarity, what I can do is I can just, I know this input is an ampersand str type, that is a string slice, so I can convert this to as str. This will also work, and same for this one, because Rust is handling too much internally for us. But if you are doing it it's the first time, don't get confused between the internal conversions. Just try to pass the exact type. So when you're converting the string type to as str, the as str is returning this type, ampersand str, so it is easy for us to do the stuff. So we now have the XOR string, and we are printing the XOR. And now for the same thing, we can say, if you want to, as I said, the inversion. Inversion is the magic of XORing. So if it's going to be decrypted, so let the input as the XORed one and key as same, then print the decrypted value like this. So what we are achieving here is this simple. We try to implement this algorithm, and this is a core of the XORing with multi-bytes key, and here we implement it, and here we try to run it here. Let's I think it won't have any issues. This is not so complicated to achieve this. Anyway, I think it has one error here because we are not using use ENV. I think this will resolve our error. Or do we need to I think ENV needs oh sorry, not like this. It's under the standard one. You have to explicitly mention like this. This should resolve our issue here. Cargo build. Yeah, it is faster because we don't use any external library, so it is faster. Now if you check under the target debug folder, there is XORing binary here. So just move to target debug and just run the XOR. If you run like this, it will say the usage is this. See, the argument 0 is replaced with XORing, the name of the binary. And now we say input is just like the encryption, and the password is secret, just like on the demo that I showed you on the PowerPoint. Try this and see, it's not printable character inside the terminal, but you can see the decrypted data is same. So the XOR value is up to here, but it's not. I think it might be non-printable characters in terminal. That's why it's showing like this. And yeah, but it worked because we tried to decrypt the value with the XOR value, so we got it back. The inversion happened here, so it works. So that's all about XORing in Rust, and hope you understand the algorithm and how it works. And next we are moving to the interesting part of this that I never did discuss before. Even my previous channel I closed. As a AES part, AES-GCM. So now you know how the XORing work, and it is important to know how the XORing work because AES-GCM's core encryption is happening using XORing. But before doing the XORing, it does a lot of stuffs. So let us explore that now. So what exactly, and if you know the cryptographic part of, if you ever tried any cryptography stuff before, you know cryptography was mostly about hiding your data just for confidentiality, but modern cryptography offers some extra features. It not only encrypts your data, but it offers integrity of data. That's what AES-GCM is doing, and it's called the advanced encryption standard in Galois counter mode, and it's mostly used in most of the modern TLS implementation deployments, but nowadays it's not the one that is used. There is another algorithm, it's better than this one, but still it is used more places, and it works on the AES CTR mode, counter mode, and that provides confidentiality part, the privacy. And the GMAC, the Galois message authentication code, that provides the integrity. So how, don't worry about these terms. I will explain in deep how these things work and how we can achieve it using Rust. And as I explained, it solves two problems simultaneously: confidentiality and integrity, authenticity, of course, because it is not only encrypting the data, but it keeps the data integrity by calculating a tag after the encryption. So yeah, let me explain how it works. So this is a H factor, or the H key that is used in here. Before any file is touched, I mean the initialization line, this is the package that we are going to use in Rust for creating this one. This part performs critical mathematical pre-computation. What's the logic behind this one is, it takes your 32-byte key and encrypts a generic block of zeros using standard AES. I know you get confused here, but let me explain. Like, the main thing here I'm going to explain here is a CTR mode, where the XOR stream, just now we did how XOR is done. It is used inside this AES-GCM. It encrypts 16 bytes of blocks, but files are not always multiplies of 16 bytes. So the CTR mode turns AES into stream cipher, so it can encrypt data bit by bit. And there are a lot of other terms connected to this one. It uses a nonce plus a counter. Nonce is nothing but number used only once, and a counterpart is a 4-byte counterpart. Nonce is normally 12 bytes, and it adds a counter with a 4 bytes, so it creates a 16 bytes, and that 16 byte of piece is used with your password to create something called random noise, and that is the output of that is a key stream. I know you may be a bit confused on this part. Let me explain in detail with an example. And the problem, before going deeper into that, the problem with the block limitation for the previous one, the AES block cipher, was if you like it hard to divide your data into 16 bytes of chunks. And maybe suppose if you had 20 bytes of data, the block cipher was dividing that to two pieces, first 16, then another 16, but it was the second part has only 4 bytes of data, so the remaining 12 bytes was filled with some random value that was called padding. So that padding was a headache. That's why this part came up, like the CTR mode, the counter mode. So how it works in CTR mode, yeah, this is how. So here I try to explain in detail as much as I can, because I understand it in this way. So imagine you have a 20 bytes of data, and the AES-GCM engine knows it needs 2 blocks of noise. That means it has to see, normally in the previous one it divides into 16 bytes of data, because the second part after the 4 bytes, the 12 bytes will be filled with padding data. Here it doesn't do that. What it does is it creates the first block with the initial 16 bytes. Then the engine takes your nonce. We have to create a nonce for this one, and it takes your nonce, the first 12 bytes, and appends a counter. A counter is going to be 4 bytes data, so it's going to be 16 bytes. So then it runs this through the AES machine using your key. So here is a catch. You have, suppose you have a password, and password must be converted to a 32-byte key, and that 32-byte key, and that 32-byte key is used here with the 16 bytes of nonce plus the counter. So what's the output of that? It spits out another 16 bytes of random noise. So you don't need to worry about this part because it's done by the engine. You just need to supply your key and the nonce, and the counter and all other stuffs are handled by the AES engine part. You should understand this one, how it works, otherwise it will be difficult for you to achieve something using this one. And I don't think there is no meaning of using it just without understanding the key part of this one. So the XOR part comes here. So now we have a 16 bytes of random noise. The random noise is done using the nonce of first 12 bytes, then a counter 4 bytes. Then it runs through the AES machine using your key, that the password that you supply normally. Then you got the 16 bytes of random noise. So and finally the actual encryption happens here. That actual encryption is just an XORing. It takes the first 16 bytes of actual data, like the actual message that you are trying to encrypt. It takes the first 16 bytes of that and XORs them with this noise. That means the noise that we got after this process. Did you get that? That means you have to supply 12 bytes of nonce. Then the AES engine will add a counter 4 bytes to that. Then it takes your key. Using your key, it runs the AES machine, the engine runs an operation for you. Then it gives you a 16 bytes of random noise. That 16 byte of random noise is XORed with your actual data. So your actual data is encrypted using the 16 bytes of random data. I hope that clears it. Now we have the 16 bytes of ciphertext. So what happens on the second block? The other mode, the previous AES one, as I mentioned, it needs another 16 block. Even if your data is less than 16 byte, it needs another 16 block. And in this example, if you consider the previous one, it fills we just have only 4 more bytes. So for the previous version, it was filling the remaining 12 bytes with padding data. But here it doesn't do that. The engine takes the same nonce but changes the counter to 2. So now we already encrypted our first 16 bytes and second 16 byte, and it again scrambles through the AES machine just like the previous one, and we get another 16 byte of random noise, and that's a block number 2 key stream. And finally you only have 4 bytes of data left. In this example actually we consider only 20 bytes. So already 16 byte encrypted and remaining 4 bytes. The engine takes the first 4 bytes of the new noise. So here is the catch. It's not going to consider, even though we are getting 16 bytes of random noise every time, it is not going to take this entire 16 bytes for us because we have only 4 bytes of data left. So what it does is it takes the 4 bytes from the random noise and it XORs them with your remaining 4 bytes data, and it throws the other 12 bytes of noise away. So it won't consider the 12 bytes of random noise because we don't need to use that because we have only 4 bytes remaining to encrypt. Hope that clears it. If you don't understand it, just try to understand that part in depth because it needs that concept in you before we move into any other even if REST AES-GCM engine is doing a lot of stuff internally for us, you should understand what XL is doing for us. In a block cipher like the old CBC mode, it would have been, as I mentioned, the 12 bytes of junk data because it always needs perfect 16 bytes of data to encrypt something. But here we are not doing that. In CTR mode, the GCM uses what exactly the input is, we are getting the exact output. That's how it works. And for this implementation, we have to go through some kind of stuff. The first one is PBKDF2. It's called password-based key derivation function. This one is actually it's not related to the AES-GCM implementation stuff, but it is needed because most of the time the user supplied passwords are not good enough to be a 32-byte data. So suppose imagine we are giving this as a password. Of course, this is a short password, is not 32-byte key, so they don't have enough bits to fill AES-252-bit AES key. Actually, it's 32-byte we need. So what we need to do is, it takes 3 parameters and puts them through the PBKDF2 engine. The first thing we need is the password. Second thing is a 16-byte salt key. Salt. This salt ensures if 2 users have the same password, their final keys are different, even if 2 users have the same password. And of course, if you are familiar with the rainbow table attacks, it prevents that. Rainbow table attacks and other stuff I will discuss later, but just for your information, the salting is the prevention of for rainbow table attacks. It makes attackers harder to crack the passwords. And the third parameter it takes is iteration. Normally it is recommended to do this number of times hashing, because the logic is nothing but it's like if you hash it more, it doesn't mean functionally for a user it doesn't take much time to hash it, but for an attacker to guess a password, it makes them to do more work to crack the password. Sometimes it may not be possible to achieve using normal machines, but yeah, it's not quantum prevention, but for using a normal machine it won't be possible to achieve it. And there are some other terms you should be familiar with. It's called AEAD, Authenticated Encryption with Associated Data, and this is connected to the AES-GCM, and here is the cache for this one. This is a Galois tag, and this is very important to understand this one. AES-GCM is an AEAD. Why? Because it's not like the previous versions of AES, the CBC, because it has that what is called the integrity checking option. It's not only encrypt the data, but it also offers an integrity check. It takes every block of ciphertext produced and multiplies it in this maths, actually even I'm not that much familiar with the mathematical computation of this one. It's a complex algebra using a special hash key derived from your main key, so it does a lot of stuff internally for us. And what it does, the final result is actually every byte is every byte is encrypted, it produces a 16-byte of authentication tag. So that means not every byte, after the very last byte. Like that means when you are trying to encrypt it using the AES-GCM, some data we have to keep it inside the file, the encrypted file, to help us to decrypt it with the key that we supply. Why? Because this is the way that AES-GCM works. It has a tag that offers an integrity check. During encryption, the tag is calculated and tagged into the end of the file. So there is a 16-byte of data that is attached to the end of the encrypted file or content to ensure that's a tag, and it ensures the integrity of the data. And during decryption, this tag is calculated and tagged onto the end of the file. During decryption, the engine recalculates the tag from the ciphertext. So, and fortunately, we don't need to do this. The AES engine that is offered by Rust is doing this for us, so you don't need to worry about this one. But you should understand this part. Like All these things are important when we're trying to use the AES-GCM part, even though we are using the high level part of it. When you are trying to access the functions inside the AES-GCM, you should be familiar with these things. So this is the chain of action. Normally password that the user supplies password that is salted with the PBKDF2 function, and it returns a 32-byte key, and a key plus nuns is going to the AES-GCM engine, and engine generates a key stream, a noise, and XORs it with the plain text. And these things we don't need to worry, because when we call an encrypt function, it does it for us. And same time the GMAC math happens and the ciphertext and builds a 16-byte tag, and the output binary any binary file containing any file of AES-GCM will have the salt plus a nonce plus ciphertext, then a tag at the end of it. So when we are going to decrypt, actually we have to retrieve all these things. We know how many bytes we are writing, how many bytes on the nonce, how many bytes on the salt, and how many bytes on the tag. As I explained everything, we need we have a tag of 16 bytes and 12 bytes nonce, and a salt of I think 12 bytes. How many? I forgot that. 16 byte of salt and 12 bytes of nonce, and another. Then the actual encrypted text comes, then a 16-byte of tag. You should know this if you want to decrypt it. Of course, we need the password for that, the key, master key password for retrieving all these things. The PBKDF2 makes the password strong. As I said, if you are normally human passwords are very weak and maybe less characters than 32-byte. So this will help us to create a strong 32-byte password for the AES CTR inside the GCM engine, so to make the data authentic. So this is how the AES-GCM works. If you have any doubt on any of the stuffs I explained here, try to try to rewind this and try to understand how it works. There's no need to, maybe you don't need to understand this one. So if it's not for you, you don't need to. But I strongly recommend, if you want to learn something, just try to get it completely how it works. So, and this are the components, the nonce, 12 bytes nonce, and as I said, 4 bytes of counter for every block, and a password key stream is 32 bytes, and maybe if it's an example, say 20 bytes of data. This was based on the example that we discussed, 20 bytes of data, input data, what happens on everything, every step, and 16 bytes of tag at the end of the file. This is how the AES-GCM works. I know it's a lot of theory. Let's try to do it in practical way, and this will be a challenge. So even though AES-GCM, it's AES-GCM, we need a lot of dependency for that. I will show you what are the dependencies. Let us close this and create a new one. So let us mkdir AES-GCM. Oh, sorry. Remove AES. We have to use the cargo for that. Cargo new AES-GCM and cd AES-GCM, and try to open that. I already tried this so many times to get familiar with this one, so I'm a bit okay to with the stuffs. And there were so many issues on the versions, especially with the random stuffs. There's some Rust grades. think here we need AES-GCM, yeah, this version. And till now we didn't add any external libraries to our project, and this is a way to add. There's a file called cargo.toml. You can come under the dependencies, you can add this. It's as simple as that. And the next one is PBKDF2 that we already discussed what it does. PBKDF2, and this one is the version. Copy this, and the PBKDF2 is actually connected with the SHA for the hashing, and some other, I think SHA 256 or something it is using. For that it needs SHA 2 package, and as I said, I already tried this so many times before. I'm just trying it again for the demo. And here was another one. We were discussing about the random number generation, and there's a package here in this one. Unfortunately, this version, when I was trying to use the way I was using, it had some issues. So here, after a lot of discussion with the LLMs, I confirmed version 8 will work for us without any issue, but still version 9 will work. I think we need to do some tweaks on the code. Maybe after that it will work. So here what we're going to do is, what I'm planning is just create another command line argument function. So it's going to accept whether we are going to do encryption or decryption, or and the password for the encryption or decryption, and the file path. Actually, we are going to do a file encryption and decryption here. So what my plan is, like after this XORing and AES-GCM, we will try to use it in real world cybersecurity testing cases, like encrypting your shell codes. Yeah, that I will discuss on next project. So this project we are going to achieve the file encryption and decryption using AES-GCM. We start with the normal argument stuff. So let's have vector of string, and now we have all the arguments, and the usage must be we have to mention whether it's going to be encryption or decryption, and then we have to supply the password, then we have to give the file. So file path. So what it's going to do, it's going to do the operation according to our user choice. So we need 1, 2, 3, yeah, 3 parameters we need. So the total number of parameters must be must be 4. So if it's going to be, 4 including the argument 0. Argument 0 is always the name of the program. So it says some foolishness, but we just use this. This is going to be encryption or decryption. Then we say password, and say file path. And return. Now we are going to take the mode is, here the difference, like the previous one we were trying to get the clone to own the string. Now I'm just taking the reference to the string. We should be familiar with all these techniques in Rust, and we discussed this very deeper in the first video. So if you have any doubt on that, please refer the first one. Here I'm just taking the reference to the arguments, and we got all these things. So now we need the actual data to encrypt. So I can say it's file data or something. Fs.read, and there's a standard way of doing this. You can say file path, and here I'm not going to use unwrap. Instead I'm going to take the question mark. What the question mark does is very interesting thing. There's something called result type in Rust. It's called an enumerator. So it has two members, OK and error. When we use question mark, any of the result type, if the operation is successful, you get the underlying value. That means you get the actual file data. But if there is any error, that error will get returned. So it's very simple, and the program will terminate from there. It won't proceed. So it returns whenever it sees an error from that, because now it's in main function. Yeah, definitely it's going to stop, and that's a specialty of question mark. It's nothing but it's called result enumerator. Okay, if you don't understand what result enumerator is, I will try to explain it in some other video. I think I may need to explain it now itself, because if you do this here, it may show some error. See, it is showing error now. It is because we don't use it here. Use stdfs. Is it resolving? See, now the question mark is showing error because this we are using inside the main function, but the main function doesn't have any return type here. So what you have to do is you set a return type for this one, and this return type must be a result, and I'm just returning a normal return type for this one. No, don't worry about this box dynamic stuff, just make it simple now, and we will discuss the box type later. So what it is just an OK result. As I mentioned, result has an OK and error type. Now the error type are defined as a standard error type. Okay, let's define the standard IO error type. Now I know what it is, but let me think it will. Okay, then this will be an issue here. So here better I can exit the this part, so it won't return anything. Now it is an error. Yeah, why? Because even though we are returning, the function is not returning any successful value here. So now it resolved the issue. Now issue is here. So I think we need process here. Yeah, these things are very basic. If you are familiar with any languages, just you need to import the packages. Oh, sorry. Sometimes the C# thing comes in my code. You have to use the double colon value here to access the functions inside any package in Rust. Well, now the syntax issues are resolved. So now what we can do is I can introduce you another thing in Rust. It's called match. Match is kind of a switch case scenario, but it's much more than the simple switch case in other languages. So here I'm going to do a match on the mode. Yeah, of course, mode string. String means we are converting to ampersand str, and if it's going to be yeah, let it be. So match is nothing but it takes if the result of the mode is ENC, and then I'm going to do this. Yeah, I'm going to do the encryption part here. Did I? Yeah, this one, this part. And if it's going to be the DEC, I'm going to handle DEC here. And the most important thing, yeah, it came here. It's not like other languages. You should tell Rust, you should explicitly tell Rust what to do if the mode is not either ENC or DEC. If you are not going to do that, it's going to compiler is going to complain. It won't build. So you have to explicitly mention using the underscore, and yeah, this is going to handle anything apart from the underscore is going to handle anything apart from the ENC and DEC. It's going to do this one. So we say this again to the user and we exit. That's it. So here is going to be the core part now. How do we encrypt it? So as I mentioned, we need a salt, and that is a 16-byte salt, and a none bytes of 12 bytes. Then we need something called a random generator, and there's a package in Rust. It's called random. That's what we use already included here. So we have to use all those stuffs here. So let us start with the salt key. Okay, it should be mutable because we have to fill it. What I'm saying is, yeah, there's a way to initialize the values of an array. It's like this. If you say 0 16 is going to create a 16-byte array, but initialize with zeros. Then we need A is very smart, but it's wrong. Let the none bytes be the same as U8, because we already discussed this one. We need we are going to use none bytes of 12 bytes and the salt of 16 bytes, and then we need to fill this using random value. For that we have something called AES-RNG that is helping us to create it's like operating system random generator. So it is well tested and it is recommended to use that for random generations. So we are going to use that. For that we are going to create a random, just say it RNG, and this is another Rust usage. We don't need any, because if you go to the documentation for AES-RNG, I think it's declared as unit struct, so you don't need to create any other stuff to create an instance of AES-RNG here. So I just declared this one, the RNG variable, using the AES-RNG type. So now I had to fill the bytes of the salt and the none bytes. So RNG dot fill bytes. First I had to fill the salt, and yeah, you can, if you check, you can see that it's a mutable reference that it accepts. So RNG dot fill bytes to destination is now is nuns bytes, and same, it is mutable reference. Is it correct? I think it's correct, but it's showing Oh no, I didn't declare this as mute, so it should be mute. So now we have, as we were explaining, we need even here we were talking about this one. We need a salt, nuns, then the ciphertext, then the 16-byte tag. That tag actually we will handle later. I mean, this is handled by the AES engine itself. So we now need the other things to do, the core part of this one. So now we have a password actually, and as we explained, the user supplied password must be converted to a 32-byte array. So we have to do that now. Let mute just say key bytes or something. Yeah, let it be 32-byte initialized with zeros. Yeah, the good thing is AES, the AES suggesting this for us. Yeah, this is the exact function that we need. We need to tell the PBKDF2 we had to use the PBKDF2 HMAC function to do the hashing for us. So for that, as I explained in the slides, we wanted a password, we wanted a salt, and the number of times it needs to be done. So here I'm taking here the password, either you can convert the password here as bytes or here, I mean the PBKDF2 I'm just taking not this one, let it come later. Let me explain this one. Now the password has the bytes, so we have actually this one is accepting a password reference. If you go to the documentation of this, it will be easier for, I mean, otherwise it will be very confusing for what should be the input of these HMAC function, I mean HMAC and SHA-256 hashing option. It needs a byte array, then it needs our salt, then the number of times, and as I mentioned, I was explaining this on the PowerPoint. We are just making it harder for cracking, and yeah, of course a mutable reference to our key bytes. So the result of this one is we will get a 32-byte random key bytes. After this, 32-bit random key bytes means it's going to fill and it's going to do the computation for us, and it's going to convert our password to a 32-byte array that is suitable for the AES-GCM. So the next one is let make it as a cipher value, and yeah, AES-GCM, and use the so instead of I think this A is suggesting something like this, and if you go to the AES-GCM documentation, you can see a lot of ways to generate the key. So suppose, imagine I'm going to take this part, let delete this. This has a lot of other options inside the new. The one I tested was like there's a key and AES-256-GCM, where is GCM? Yeah, you can click this type, and from there's a from _ slice method. this is the one I tested, and yeah, it worked well for me. So that's I'm just suggesting you to guys, and you can try with the other options. On the documentation they have mentioned different ways of creating this cipher part. So now we have the cipher, XOR cipher with us. And so what exactly the next step as per the encryption part is like? Now we need our nonce bytes to be we have to supply the nonce here. That's going to be used with the AES-GCM that we means you remember that the number of bytes that we were discussing, the 12 bytes of nonce, then 16 bytes of sold, 16 bytes of sold, 12 bytes of nonce, then the ciphertext, then the tag. So here we have to create the same order. I'm going to say the nonce here. Oh yeah, this is the one actually I had to use here. I want to use this one, nonce from slides, and we are going to use the already filled nonce bytes here. So we have now a nonce type that is created from this one. So this is going to be used inside, this is going to be used in the AES part. So now we are going to create the ciphertext. Ciphertext equal to take the cipher dot encrypt, and as I mentioned, we have to give the nonce and the actual data that is going to be encrypted. And okay, I think you can, instead of this unwrap stuffs, you don't need to use unwrap again here as a trap. It's a trap, in fact. Yeah, that's what I feel most of the time. Sometimes it crashes without any, but if you say it to some Rustaceans, they'll kill us, because it's one of the ways. Just because, and I'm just getting familiar with this error stuffs in this one. Yeah, there's a method called as reference, so that will be safer for us. And this was the working one I tried. So now we actually all the stuff that we discussed now till now is handled by the encrypt function. The slicing of the stuffs and creating the key streams and XORing it, all these things are handled by this function. And now the rest is like, we have to write. I'm going to try to, I'm not going to do any new file, I'm just rewriting the same content with the ciphertext, and no need of unwrap. I'm just using the question mark here because we already have a return type here, so it's fine for us. So here I think we did almost everything that we wanted to do. Oh no, before writing the data, we we didn't finish actually. We created the nonce and we used it inside the encryption, but we didn't create the actual output data. We have to prepare the data. Actually, we are preparing the data. It's not something this is going to do the magic for us. After creating the ciphertext, we have to explicitly create the data. I mean, the right. We had to explicitly write the salt, the nonce bytes, and the ciphertext. The tag will be automatically added to the end of it, but we have to write other three. So what we have to do is, another thing I'm thinking is, like, I think here we had to handle this one. The encrypt is returning a result type, I think. So yeah, there is another way of handling the result type. I mean, not the result type, but if you, instead of unwrap, actually it's always better to do an expect method. Expect is nothing but almost same effect, but at least you should know. I mean, you will come to know what exactly happened. Here I'm safely doing this one, but if in case, just to ensure that if in case something happened to our encryption, just we get a message that it failed. So the next thing, what we have to create another vector, what to say, byte of vectors to write our container value. So our container means the output that is going to be created by us. We have to manually do that, and we should know what exactly we are writing there. At the time of decryption, we have to take off the same values. So what I'm going to do is, I'm just saying that let mutable value of say output a new vector, then I'm saying output dot, yeah, this is the method, extend from slice. We have to add the salt, and we have to add the nonce bytes. Then we have to add the ciphertext. Then we can or instead of the ciphertext, actually we have to write the output of this the new vector, because we need that vector on the encrypted file, because when we are going to decrypt it, actually we have to do the reverse stuff. We have to take off the first 16 bytes as sold, next 12 bytes as our nonce bytes, then the rest of the stuff as our ciphertext, then exclude the last 16 bytes. Like, actual ciphertext is before the last 16 bytes, and after the nonce bytes, because we are generating that in that way. And after this I can say print maybe encrypted file. So now the encryption part is done. Actually we did all this. If it's confusing for you, maybe because you are not familiar with the parameter stuffs and the reference type. So what I'm suggesting is just read the official documentation of that, and even this one. There are so many other ways to achieve this. This is one of the ways, especially the key generating here is there are so many other ways to get the key type. So you try with those things and let me know which are the other things that work for you. Now we have encrypted the file, and now the next is you have to do the same decryption for us. So AI is already suggesting that for us. So we have to take off. Let me check this code because I don't want to type it. It's going to be a very long video if you type it everything. So we are taking in back the salt from the file, the actual file data, because it's suppose, I mean, and one more thing here, When it's going to be an encryption part, the file data is going to have the encrypted this thing that we did. So we are taking the first 16 byte salt, and none bytes after that, 16 to 28, that means 12 bytes after 16. Then we are taking the ciphertext after this one. Everything is a ciphertext, but internally the last 16 byte is the tag that is used, and all these things are handled internally for us when we are going to call the decrypt. So we are creating the key bytes, and again we have to do the same hashing on the password using the same method. We create a random SHA-256 HMAC. I mean, we're going to do an HMAC function inside this, and the same operation. We are getting the cipher using this. Then we create the same nuns. Then we decrypt using the nuns and the ciphertext, because we see, you just get the connection between these. We create a cipher using the key bytes. So this will work only if the password is, this key bytes is filled using the password. So these things are connected. If any of this is wrong, it won't work. So the password is converted to 32 byte array that is supplied to the PBKDF2 function, the HMAC thing, and then that is used to create a cipher from the key bytes, and we create a nonce after that, and then the cipher is using to decrypt it. So the decrypt part is going to handle the integrity check for us. We don't need to worry about that one. And after that we write the file path, the plain text, and we return it. Then we say print decrypted file path. I think this will work, but yes, some error here and there. Oh yeah, a lot of use issues. So you have to use a lot of stuffs here, and the first one is use I think AES-GCM. Yeah, this is suggesting, but when I was using this one, we need a lot of other stuffs. I think we need as I already discussed this one, AEAD was there, and inside AEAD we need AEAD, then the key in it, then we need AES-256-GCM, the nonce, and yeah, the key. I think it was suggesting the key. We need all these things because we AES-GCM. I got all these things from the official documentation, so if you just go there, it will be easy for you to get that. Yeah, this came automatically, random core RNG-OS ring we used, and I think RNG-OS ring. Then after that, yeah, we need the SHA use SHA-2. We use a SHA-256. Did we use that SHA-256? I think, yeah, we use the SHA-256, right? Yeah, but I think we directly use it here. It may not be needed. Yeah, it is not needed. I think let me let us build this terminal cargo build. See, now I mean now it's far better than the old versions. On the old versions of Rust, actually, when we are trying to add external libraries, it was taking huge time to compile, but now it is far better. I think it's finished. Let me check on that debug. See, it's an AES-GCM binaries here. So what we do here, let me create, instead of making it complicated, let me create testdnc.txt file. This data is for testing the encryption using AES-GCM. So now what I can do is I am just go to the folder, debug folder. So let us run the AES-GCM, just see how it works. Yeah, it needs I'm saying ENC, and my password is going to be password. Okay, this is our password. So, and just for testing, and let us say the file path is test enc. Let us see. Oh yeah, it encrypted the file. It worked well, in fact, without any issue. See, the content is encrypted now. So what if we do the decryption? If the decryption fails, it is going to be another nightmare. Oh, nothing failed. Yeah, because the fact is that I did write in a different ways and other stuffs, like the same thing I try in different ways. Now it is a new way for me. So many things I learned from, even from this one. There was another ways I was writing the same thing, because this is really interesting, especially the encryption and how it works is really interesting. But let us check whether the file is correct or not. If it's going to be, yeah, see, this is exactly the same kind of data that we had. So we successfully encrypted and decrypted the file. And you know, learning encryption is really important for if you are in cybersecurity or any other field that's connected with you in cryptography. This helps you to understand so many things, especially how ransomware works. And yeah, definitely I have more projects in my mind to cover in Rust CLI this series. And for this series, I mean, not for this series, for this video, this is end. And I strongly suggest to you, if you like the video, try to subscribe and stay tuned. We will come up with more stuff for everyone, not only for cybersecurity, for every programming stuff we will come and cover. Try to explain on my own ways what I understand, what I did learn from that. I'll try to share with you. So stay tuned. This is the end of the symmetry encryption, XORing and AES. See you soon with another video. Bye.